Ever wondered how massive apps like Instagram or Uber handle millions of requests without even breaking a sweat? Well, a huge part of the answer often lies in a deceptively simple but incredibly powerful concept, the message queue. In this explainer, we're going to pull back the curtain and show you how this one component can be a total game changer for any system you design. So let's get right into it. To really get why we need message queues, let's start with a little story. Picture this. You're an engineer, and the photo sharing app you built has just gone viral overnight. I mean, this is the dream, right? The thing you've been working towards. Except it's also quickly turning into a complete nightmare. Your success is literally your downfall. Users are complaining that uploads are slow, your servers are crashing left and right, and the beautiful architecture that worked perfectly for 1,000 users, yeah, it's crumbling under the weight of millions. Let's really dig into what's going wrong. Okay, so there are 3 huge problems here. First off, latency. Your users hit upload and they're just stuck staring at a spinning wheel while your server tries to do everything at once. Resize the image, apply filters, run moderation checks. It's a terrible experience. Second, the whole system is incredibly fragile. If, say, the filter service crashes mid-process, the entire upload fails. All that work is just gone. And finally, you can't handle traffic spikes. Your app gets featured and bam, you go from 50 uploads a second to 50,000. Your servers are totally overwhelmed, requests start getting dropped, and your system just falls over. So, how do we fix this mess? This is where the sheer elegance of the message queue comes in. See, the solution isn't just to throw more powerful servers at the problem, it's about fundamentally changing how we think about getting the work done. So instead of making the user wait for all that heavy lifting, your server does the absolute bare minimum. It saves the photo, and then it just drops a simple little message into a queue, something like, hey, process photo 456. And then it immediately tells the user, upload complete. All the slow stuff like resizing and filtering, that'll be handled in the background by other workers who are just pulling jobs from that queue. And the impact here is just dramatic. Seriously, look at this table. In the before column, you've got high latency, total process failure on a crash, and an overloaded system. Now look at the after column with a queue. Latency, super low, because the user gets that instant response. Failures, they're totally isolated. If one worker crashes, no big deal. The message just gets redelivered to another one. And those traffic spikes, the queue acts as a giant shock absorber, a buffer, soaking up all that load so no work is ever lost. It solves all 3 of our initial problems in one go. Now, the magic that makes all of this work is a core principle called decoupling. It means the part of your system creating the work, we call that the producer, is now completely separate from the part doing the work, the consumer. They don't talk to each other directly. They only communicate through the queue. And that is huge, because it means you can add more consumers when you're busy or scale down producers, and neither side needs to know or care about the other. They can operate, scale, and even fail totally independently. This is probably the best analogy for it. The message queue is just like that ticket rail you see in a busy restaurant kitchen. The waiter, that's our producer, slaps an order on the rail and is immediately free to go serve another table. The cook, our consumer, grabs that ticket whenever they have capacity. That simple ticket rail decouples the waiter from the cook, allowing the entire restaurant to run smoothly and efficiently, even when it's slammed. Okay, so we've got the why. We know why we need queues. But what's actually happening under the hood to make them so reliable? Let's get into the mechanics that make them so incredibly robust. This is a classic question and a critical failure scenario. So a worker, a consumer, pulls a message to start processing a photo. Halfway through, the server it's on crashes. Now, if the queue deleted that message the second it was pulled, that user's photo would be gone forever. And obviously, that is not acceptable. And the solution is a clever little thing called an acknowledgement, or ACK for short. Here's how it works. The queue doesn't actually delete a message when a consumer pulls it. Instead, it just kind of marks it as invisible. It then waits for the consumer to finish the job and send back an ACK signal that basically says, hey, I'm all done with this one. You can delete it for real now. If the queue doesn't get that ACK back within a certain amount of time, it just assumes the worker crashed and makes the message visible again for another worker to pick it up. Simple, but brilliant. No work is ever lost. Now, this brings us to a really crucial concept, delivery guarantees. The system we just described, the one that uses acknowledgements, provides what's called at least once delivery. The queue guarantees every single message will get processed. But there's a trade-off. What is it? Well, it might get processed more than once, right? If a worker crashes right after doing the work but before sending the ACK. The alternative is at most once delivery, which is more like fire and forget. A message might get dropped, which is only really okay for non-critical stuff, like maybe some analytics data. So that at least once delivery gives us a new problem to solve. How do you handle those potential duplicates? You can't, for example, charge a customer's credit card twice. The answer, and this is a key term, is idempotency. You have to design your workers so that running the same job multiple times has the exact same result as running it just once. For example, an operation like set user photo to X is idempotent. Do it 5 times, the result is the same. But an operation like increment post count by 1, that is not idempotent. The industry standard is to always use at least once delivery and then put in the work to make your consumers idempotent. All right, we've nailed down the fundamentals. Now let's level up. We're going to explore some of the more advanced concepts that you'll absolutely need to know if you're building a real-world system or, let's be honest, for that next big technical interview. So, when should you be thinking, aha, I need a message queue here? Well, here are 4 crystal clear signals. Number 1, you're doing asynchronous work where the user doesn't need an immediate result. 2, you're dealing with bursty, unpredictable traffic, and you need that buffer. 3, you need to decouple services that have totally different scaling needs. And 4, you absolutely require reliability. You cannot afford to lose a single piece of work. If you check those boxes, a queue is probably your answer. Okay, here's a really tricky operational problem you'll eventually hit. What if a message is just bad? It's corrupted or malformed. Every single time a worker pulls it, that worker crashes. The message gets redelivered, the next worker pulls it, and it also crashes. This is what we call a poison message, and it's a huge deal because it can block your entire queue, preventing any other legitimate work from getting done. The standard solution for this is the dead letter queue, or DLQ. It's pretty straightforward. You configure a retry limit, let's say 5 attempts. If a message fails to be processed 5 times in a row, the system assumes it's a poison message. Instead of putting it back in the main queue to cause more chaos, it moves it to the separate dead letter queue. This immediately unblocks the main queue so work can continue, and later, an engineer can safely go look at the DLQ to figure out what went wrong without halting the entire system. Now for a really big scaling challenge. You have to remember, a queue doesn't actually solve a capacity problem, it just delays it. If your producers are consistently creating work faster than your consumers can process it, that queue is just going to grow and grow forever until it runs out of memory and everything crashes. So when this happens, what's the playbook? What do you do? Well, you've got 3 main strategies. The first and most obvious is to auto-scale your consumers. You monitor the depth of the queue, and if it gets too long, you automatically spin up more worker instances to help clear that backlog. Second, you can apply back pressure. Think of it like putting your thumb over the end of a hose to slow the flow of water. You have to signal the producers to slow down, maybe by temporarily rejecting new work if things get too crazy. And at the absolute bare minimum, you need to set up alerts so that you know when your queue is growing out of control. So far, we've mostly been talking about concepts and principles, but what technologies do engineers actually use to build these systems? Let's take a quick look at some of the most popular options out there in the wild. 3 big names really dominate this space. First, you have Apache Kafka. The best way to think of Kafka is like a durable, replayable log. It's an absolute beast built for massive, high-throughput data streams. Then you've got Amazon SQS. This is your simple, fully managed, get-the-job-done work queue, especially if you're already in the AWS cloud. And finally, there's RabbitMQ. Think of RabbitMQ as a smart post office. It gives you really powerful and complex routing options to direct your messages exactly where they need to go. And that brings us to our final thought. You see, in distributed systems, there are always trade-offs. For instance, you might decide to route all messages for a specific user to the same worker to guarantee that their actions happen in the correct order. But what if one of your users is a massive company that generates a ton of traffic? You could accidentally create a hotspot where one worker is totally slammed while all the others are just sitting there idle. So the question I want to leave you with is this. When you design your system, which is more important? Guaranteeing strict ordering or making sure the workload is perfectly and evenly distributed? The answer to that will define your entire architecture.
Thank you all for watching this here video. Please like and subscribe.